Welcome back to the wonderful world of physics. This is chapter 15 on fluid motion. This section is 15.2, hydrostatic equilibrium. Back in chapter 12, we learned about static equilibrium, which is the state in which a system at rest remains at rest because there's no net force to accelerate it and no net torque to start it rotating. In this video, we're going to look at hydrostatic equilibrium. For a fluid to remain at rest, the net force everywhere in the fluid must be zero, and that's what's called hydrostatic equilibrium. In the absence of any external forces, hydrostatic equilibrium requires that the pressure be constant throughout the fluid. So hydrostatic equilibrium is defined as the case in which the fluid is at rest, so the net forces add up to zero throughout the fluid. In this picture at the top, we see, imagine that this is inside a large mass of fluid, and we take this dotted line. This is a chunk of the fluid inside. So imagine a few cubic centimeters of water that are inside a swimming pool of much more water. And if you imagine that the forces are unbalanced, like you can see in this top picture, then it will start to accelerate to the left. But down at the bottom, we can see if all the forces are equal in all directions, then the forces will be equal and we'll have the case of hydrostatic equilibrium. Now, let's think about that last picture. The forces are the same. You can see my purple vectors there. They're the same in all directions. But then imagine that there is gravity added to this, and that's my green vectors right there. Well, if we add gravity, then this chunk of fluid is going to accelerate downward. So in order to have it just sitting there in hydrostatic equilibrium, we have to have something that balances gravity. In order to balance gravity, there must be added fluid pressure pushing upward. And that's what we're going to talk about in this video, that there is some added pressure upward. We're going to look at where does that pressure come from. Consider a mass in a fluid, and the mass, we can think of it very small. We can think of it a mass element, dm, and it has some surface area A. I've drawn this cylinder right here, and it has a thickness of dh. And I could have used a mass of m and a thickness of h, but we want to be able to imagine that this is very small. We can imagine a thin sliver. Now, we can think that there is pressure pushing down and pressure pushing up, and if this is going to stay not moving, then those need to be equal to each other. You see these three force vectors, the one from the pressure pushing up, the one from the pressure pushing down, and then the weight. Let's talk about the weight. Instead of mg, I'll call it dmg. And I want to go down here to where my marker is. The density of the cylinder is mass divided by volume. And that means that its mass is density times its volume. And so using the notation of calculus, those mass elements, let's call it dm, is equal to the density rho times, and instead of volume, let's use A times dH, the surface area times the height of that cylinder. And now I'm going to go back up here with my dotted line arrow, and dmg becomes rho A dHg. The condition for equilibrium is that the sum of all the forces equals zero. So up at the top, my picture actually is a force diagram. And let's apply, this essentially is F equals ma, but here F equals zero. And let's apply it. We have our pressure pushing up, and we're going to call that P plus dPA. Now there's a dPA in there because if you think back to my previous slide, there was this arrow, I said, this upward arrow, this additional pressure that comes from the fluid that must be there if this cylinder of fluid is just going to float and not be moving. So there's going to be some additional pressure, that's dP. So drawing off of my picture at the top of the screen, P plus dP times A, so pressure times area, that's the force, minus, because it's down, P times A, that's the force pushing down on the top, minus, and now we've got the weight of the cylinder of fluid, rho Ag dH, all those have to be equal to 0. Now let's simplify this. You can see that the area doesn't matter. We have P plus dP A minus PA, and that just becomes dPA minus rho Ag dH. And here I've just crossed through the A, but understand that mathematically I've factored out A and divided by the entire equation by A. And we're left with dP, which is the additional little bit of pressure that's on the bottom of the fluid, minus rho G times dH equals 0. And what this all amounts to is, when we put it in this form at the bottom of the screen, dP dH, or dP over dH, equals rho times G. Now this equation refers to the pressure changing with depth, the rate of change of the pressure as you go deeper and deeper down into a fluid. Then pressure increases, and it increases in proportion to the density of the fluid times the strength of gravity. So here's that equation that I derived on the previous screen. So dP over dH is rho times G. Again, that means the rate of change of pressure with respect to depth is rho times G. So even though on the previous screen I wasn't really referring to H as the depth in the fluid, understand that in that picture of the cylinder, it was comparing the top of the fluid and the bottom of the fluid. Essentially, that is how much deeper the bottom is versus the top. Let's do a little bit of calculus with this equation. Let's get the dH over to one side. We have dP equals rho G dH, and we're going to integrate both sides. On the left-hand side, the integral of dP just becomes pressure. And then we've got rho GH. Now this assumes that rho and G are constant. And if not, I would have had to do some integration and know how density or G, how they change with respect to H. But it's assuming that those are constant. And so we can take that simple integral and it just becomes rho GH. Now this is an indefinite integral. There's going to be an additional constant that's being added, and that's just going to carry itself over here as P naught. So this is the equation that you need to know, that the pressure somewhere in a fluid is equal to some constant pressure, and that physically is the pressure at the surface. Now, pressure at the surface, you can think if you imagine a lake, and there is pressure added as you go deeper under the lake. However, you have to understand there is atmospheric pressure. There is that 14.7 pounds per square inch that is pushing down on the surface of the lake. So that adds to the pressure in the fluid. So if you don't go any deep into the lake, you're starting at 14.7 pounds per square inch. And then the deeper you go, this part of the equation kicks in, plus the density of the fluid times G times H, which is how deep you go under the surface. So here's the equation. P equals P naught plus rho GH. And note that I wrote it works for liquids but not for gases. Because gases are compressible, that density is going to change. And the simple integration that I did doesn't work. We'll need another equation for that. But we'll use this equation for liquids. Let's look at, in the book, example 15.1. It says, at what water depth is the pressure twice atmospheric pressure? And then it asks, what is the pressure at the bottom of the 11-kilometer deep Marianas Trench, the deepest point in the ocean? Take atmospheric pressure as 101 kilopascals and the density of seawater at 1030 kilograms per cubic meter. All right, we're going to take this equation at the top. It's asking how deep, particularly How deep or at what water depth is the pressure twice atmospheric pressure? So we'll take for P, first we'll solve for H. H equals P minus P naught over rho G. And then we'll take for P 2.026 times 10 to the fifth, that's twice atmospheric pressure, minus P naught. And so up top, we're looking essentially at that the liquid, the ocean itself, has added 1 atmospheric pressure because it's at a total of 2, but the air above it has contributed 1 atmosphere to it. Okay, divide by rho. They're telling us to use 1030 kilograms per cubic meter and 9.8 newtons per kilogram. We plug those numbers in and we get 10.0 meters. So if you go down 10 meters under seawater, then you're experiencing double atmospheric pressure. By the way, if it were fresh water, the density is a little lower. There's not as much pressure, there's not as much pushing down on you, and so you can actually go a little deeper, not much, 30 centimeters more, so it's 10.3 meters to get at twice atmospheric pressure. Now for part B, we're using the same equation, and I've modified it a little bit. Recognize that the pressure under a fluid is the pressure that is being pushed on the fluid by something external. And in this case, it's going to be the air pushing down on the ocean surface, plus, and I've just called this delta P. That is the change that is contributed by the ocean surface. Now, if we want to know what is the pressure, we'll plug in. So first we've got the P naught, the air pressure, 1.013 times 10 to the fifth pascals, plus, and here we have rho GH 1030 times 9.8 times H, and it says 11 kilometers, so that's 11,000 meters. And I've kept these numbers separate so that you can see the difference. Remember in part A, when we only went about 10 meters down, it doubled atmospheric pressure. Now we're talking about going 11,000 meters down. It's going to be a tremendous amount of pressure. So we've got 1.013 times 10 to the fifth pascals. The portion of pressure that's added by the fluid is 1.11 times 10 to the eighth pascals. So whereas air pressure is 14.7 pounds per square inch, this additional part is about 8 tons per square inch. So the portion that air pressure adds is negligible. And it comes out to about 1.1 times 10 to the 8th pascals. Now, where does this pressure come from? The deeper you go, the higher the pressure. Well, the pressure is due to the burden of the fluid that is above a given point. So if you're right here where my marker is and you're under the fluid, you've gone into a swimming pool or under the ocean, you are bearing the weight of that column of fluid that's above you. That is what increases the pressure. Now, even if you're not there personally to bear that weight, then there is fluid that is down there that is bearing the weight. That's where pressure comes from. The weight of that fluid, that column of fluid, of course, is mg. M is density times volume times g. And remember that volume of a solid object, such as this cylinder, is rho AHG. And I shouldn't have called it a solid object. It could be liquid just the same. But the weight is rho A times Hg. So weight is density times surface area times H times G. The change in pressure between two different heights is weight over surface area. Again, we're still thinking about the weight of that column of fluid divided by the surface area of that column, and it's rho times G times H. Now, when we're talking about air pressure, the column of air goes about 60 miles high, so that the pressure at the bottom is 14.7 pounds per square inch, what we call 1 atmosphere. It's 1.013 times 10 to the 5th pascals. Now the thing is, we can't use this equation up top because the density changes. The air, the atmosphere is a gas, so the deeper you go, the denser it gets. Air's density goes from, at sea level, it's 1.28 kilograms per meter cubed. But you go to the top of the atmosphere, in reaching out into outer space, and it's 0. And so the calculation gets a bit trickier. You can actually use calculus to derive this. But atmospheric pressure is given by this equation. It's E, and that E is the base of the natural logarithm, to the negative 0.0000385 times h, where h is not the depth under the atmosphere, but I'm using, this is a very practical equation where it uses h as the elevation above sea level. And it's doing it in feet. Rarely in this class do I prefer to use feet and English units, but this is the standard that's used in America, such as in aviation. Pilots want to know what is the atmospheric pressure, and so this is what we most readily use. So here's the equation. Now, if you look at this picture down below, you have a column of air down to the ground, and so someone down on the ground is bearing the weight of all this air. Someone up in the top of Mount Everest isn't bearing the weight of that much air. Now you think, well, a mountain, even the tallest mountain, doesn't really go that high compared to the height of the atmosphere, but it still is a tremendous decrease in pressure because look at how the artist here bunched all these dots together. It's denser down here. So as you go high up, thousands of feet in elevation, you are getting through the densest parts of the air. So you're cutting through a lot of pressure. You're decreasing the pressure quite a lot. If you look at my drawing here, let's start on the ground, 0 feet, and that means you're at 1 atmosphere. If you go up into the foothills of some mountains, so here I've drawn the Rocky Mountains there. If you go up to 8,000 feet, so that's something like 1.5 miles, your air pressure is at 0.73 atmospheres. That means that you have cut through, just by going up 8,000 feet, you have cut through more than a quarter of the air. You're not bearing as much of a burden. Now, if you go up to about to 16,000 feet, you're only at 0.54 atmospheres. So when you're traveling up into the mountains, it gets a little harder to breathe. Now, at 18,000 feet, and I get all these numbers from using this equation at the top. You can test these numbers if you want. But at 18,000 feet, you've cut through half of the atmosphere. So you're only bearing the burden of half of the atmosphere. And that's pretty neat. You're only about 3.5 miles up. It's a 60-mile tall atmosphere. We say it's about 60 or 62 miles as it gradually thins out. But if you only go up 3.5 miles, you've cut through half of the atmosphere. You go up towards Mount Everest, so 24,000 feet, you're at 0.4 atmospheres. Go up to about 36,000 feet. Now this is where commercial airplanes fly. It's about a quarter of an atmosphere. You have cut through 3/4 of the air. You've only got a quarter of the atmosphere up above you. Now, you can't breathe at a quarter atmosphere, so airplanes that go this high need to be pressurized. They pressurize the cabin of the airplane so it feels like you're much lower and you can breathe the air. You go up to 48,000 feet. And the military fighters go up, fighter jets go up this high, and you're only at 1/6 of an atmosphere. Let's look at some very practical application. The water cooler. You're getting water, and maybe you have a lot of people, and I remember back to as a child, soccer practice. So we're all trying to get our drink out of the water cooler, and there is, you open up this spigot right here and the water, the Gatorade, whatever it is, comes flowing out. And there is a certain depth that the spigot is at, and I've shown that by H right here, the height. And the pressure of the fluid at the spigot is the density of the fluid times the strength of gravity times that depth. Now, as more and more people are drinking and taking fluid away, the water level gets lower and lower, so you get less and less pressure. So then it comes down to right about here, maybe it gets right to the spigot, and you're getting very little pressure. And there might be a lot more fluid in there, but certainly if the fluid goes below the spigot, you're not going to have access to it, so you need fluid above the spigot, and it's going to be very low pressure because you've only got that little bit of H. So what do? You tilt it. So you tilt it like this, and now, even though you haven't increased the amount of fluid, what's most important is that you've increased the height difference between the spigot and the top of the fluid. So this H carries over to give you more pressure. P equals rho times GH. So when the pressure is running low in a situation like this, tilt it, and that'll increase the pressure. Here's a neat little demonstration and experiment you can do. You have a container of fluid, and you can do this with a plastic 2-liter bottle. You can drill holes at different heights. I recommend, for accuracy, to make the holes be the same diameter, so you can use a drill with the same drill bit, and drill holes at different heights. And what you're going to see is the water will spill out, but it's going to come out faster at the lower hole. And the reason is there's more pressure down here because of that greater depth, and so it'll come out faster. There are different ways to measure pressure, whether it's air pressure or liquid pressure. Could be the pressure in a tire of a car. Well, let's look at this, how we measure air pressure. An old instrument called a barometer to measure air pressure goes like this. You have a bowl with some fluid in it, and we want to measure the air pressure. So the air pressure is going to act on the open pool of fluid, and a good liquid for this, a good fluid, is mercury. It can get messy and toxic, but because of its density, it actually makes for a good barometer, as long as you don't make a mess. But the air pressure acts on the open pool of mercury, pushing the liquid into the evacuated tube. Now, we've got essentially a vacuum up here, so we're going to call that P0 equals 0. And the greater the air pressure, the greater it's going to push the fluid up into the tube. So the air pressure is going to be P0, which is 0, plus rho times GH. And the height that the fluid is going to go as it goes up the tube of this barometer is the air pressure divided by rho G. And so you can see the numbers as I've plugged them in. Let's just say the pressure is 1 atmosphere, 1.013 times 10 to the 5th pascals. We're going to divide by the density of whatever the fluid is. So it's not the air, it's the fluid that we're lifting up. For mercury, mercury is very dense, 13.6 times 10 to the 3rd kilograms per meter cubed. Now this can be done with water, but you're only going to divide by 10 to the 3rd, and it's going to be a much taller column of water. And also in the denominator G, which is 9.8 newtons per kilogram. So the height we get is 760 millimeters, or 29.92 inches. Now, if the air pressure is lower, you're going to get a lower column of fluid because it's not going to be pushing as much. If air pressure is higher, you're going to get a higher column of fluid. And this is used in meteorology. Generally speaking, when there is low pressure, it means essentially that bad weather is coming in. If there's high pressure, atmospheric pressure, then we have good weather to look forward to. The units that we use, these are rather awkward units. Instead of using pascals or atmospheres, in meteorology, they use millimeters of mercury, or sometimes they use inches of mercury. And it refers to, if you have a setup like this, a barometer, how tall is the column of mercury going to be if the current air pressure is pushing down on it? And by the way, blood pressure is also measured with millimeters of mercury. Here's a practical application of air pressure. Drinking through a straw. When you drink through a straw, there is no sucking motion. We say that we suck through a straw, but here's what's really going on. The fluid needs to be exposed to atmospheric pressure. So this cannot be in a completely sealed container. Now, atmospheric pressure pushes down. When you, as we say, suck on a straw, what you're really doing is you are decreasing the pressure in the straw just slightly. And in order to do this, you're only decreasing the pressure by probably less than 1% of atmospheric pressure, just a little bit. So the pressure is less, and just like with the barometer that I showed you on the previous slide, where you're not getting a complete vacuum here, but you are getting a partial vacuum. And again, it's like 99% of atmospheric pressure. And so the atmosphere pushes down and up through the straw. Now, a really neat thing you can do with a Capri Sun, those little flexible packages of drinks, is when you have the straw in and it's in your mouth, blow into the straw. Instead of sucking, instead of decreasing the pressure in your mouth, actually blow air into it. What's going to happen is, while the Capri Sun is a fairly concealed container, when you blow air into it, you're going to increase the atmospheric pressure on the inside. You wait a split second, and that increased air pressure that you've just added will push the fluid up through the straw and into your mouth. Just don't choke when you do it. Another way to measure pressure is a manometer. A manometer is a U-shaped tube filled with liquid. It's used to measure pressure differences. A pressure difference between the two ends results in a height difference, h, between the liquid surfaces. So you look at this picture right here, and let's say we have a high pressure fluid that we want to measure, and we're going to compare it with the pressure of air. The greater the fluid on the left, it's going to push a higher column. Now the H, as you can see, is right here. So we've got a liquid that's on the inside, and the difference between the height, if you look at this U right here, this U shape, there's a height of the liquid on this side and the height of the liquid on this side. What matters is the difference between those two heights, as I've shown there in H. And so that difference shows the difference between the pressures. So the pressure that you're measuring on the left minus the air pressure is rho GH. And that's called the gauge pressure. So you're not actually measuring P. You're not directly measuring P by rho GH. Notice it's P minus P air. But what it is telling you is it's showing you the difference between the pressure and the air pressure. And so we call that the gauge pressure. Here's a common device, a tire pressure gauge. Use this to measure the air pressure in your tires. And you hook the part on the left to the valve on your car tire, and it will blow a bar outward. And the greater the pressure in the tire, the more force it'll blow the bar outward. Now, that pressure in the tire is competing with air pressure pushing the bar in the other direction. So it's kind of like a manometer, loosely like one, except you're dealing with a solid bar. Now, whatever it says on the meter, you notice I've drawn these little tick marks because how far the bar goes out corresponds to a certain pressure, and that is the gauge pressure. So, for example, on most vehicles, if you open the driver's side door, on the panel, there's something that gives information, what size tire the car takes and what pressure you should have it to. So a typical pressure, it's usually given in pounds per square inch and also kilopascals. Let's go with pounds per square inch, typically maybe 30 pounds per square inch. Now that is the gauge pressure. And that's the only number you need to be concerned about when filling up your car tire. However, it's good for you as a trained physicist or engineer to know that that isn't the actual pressure in the tire. The actual pressure, the absolute pressure, is whatever the gauge pressure is plus whatever the atmospheric pressure is. Now, if you happen to be at sea level, which we roughly are in Porterville, California, then 30 plus standard pressure, air pressure is 14.7, so we get 44.7 pounds per square inch. Let's talk about these unit conversions in case you need to convert between pounds per square inch and pascals. So let me take you through this. We have 20 psi, but remember in proper unit notation, that is pounds over square inches. And if I want to get that to pascals, which are the metric units, I will first convert that to it's 1 atmosphere is equal to 14.7 pounds per square inch. So let's do that. The pounds will divide away, the inches squared will divide away. We're left with atmospheres. Then I want to get atmospheres to pascals, and here we have 1.013 times 10 to the 5th pascals divided by 1 atmosphere, and you would get 1.38 times 10 to the 5th pascals. Another way to do that same conversion is we can start with 20 pounds per square inch, and then we can first get rid of pounds, turn it metric into newtons, 4.448 newtons over a pound. That'll give us newtons per square inch. Then we'll multiply by 1 inch over 2.54 centimeters, but remember we have to square that. And then we need to get those square centimeters to square meters, so 1 centimeter over 10 to the negative 2 meters. Remember to square that because it's square units. And then you will have newtons per meter squared, which is pascals. And speaking of pascals, here is Pascal's law. A pressure increase anywhere in a fluid is felt throughout the fluid. Now you've seen this equation before, and I'm giving this to you in just a slightly different context. When I showed you this equation before, I was specifically referring to the pressure, for example, on the ocean, the pressure as you go under the ocean, and you add air pressures pushing down on the surface, and it adds to the pressure. But it doesn't have to be air pressure pushing down on the surface. The point of Pascal's law is that if you add pressure anywhere in the fluid, it'll be transmitted throughout the entire fluid. So here we have this person holding a bottle and there's holes in it. And because of the depth of the fluid that the holes are at, of course, the water will spill out. But if this person squeezes, that will increase the pressure throughout the fluid, and that will increase the pressure at the holes, and then it'll come out faster. Let's do in the back of chapter 15, let's do problem number 19. And this is actually very similar to example 15.1 that we did earlier, but just to remind us of all these concepts that we've covered in this video. It says scuba equipment provides a diver with air at the same pressure as the surrounding water. But at pressures higher than about 1 megapascal, the nitrogen in air becomes dangerously narcotic. At what depth does nitrogen narcosis become a hazard? So we're looking at answering the question, at what depth under the water is pressure 1 megapascal? And again, you can refer to example 15.1 that we looked at earlier. Let's look at this. We'll use this equation. The total pressure under the fluid is the pressure on the surface, and that's what the atmosphere adds, plus rho gh. So the density of the water times g times h. We want to solve for the depth h. So P minus P naught over rho g. P is the pressure that the problem gives, 1 megapascal. But then we're going to subtract away the contribution that the air has made, 1.013 times 10 to the 5th pascals. Divide by the density of the water. Now you can choose whether to use fresh water or seawater. I've just gone with fresh water here, 1,000 kilograms per meter cubed. But if you're using seawater, you use 1030 kilograms per meter cubed. And really, it's only going to change our answer by a couple of meters. and 9.8 newtons per kilogram for gravity, and we get an answer of 92 meters. And here is an outstanding practical application of Pascal's law. This is example 15.2. In the hydraulic lift, you can see that picture I've drawn. A large piston supports a car. Now that's the piston on the left. I haven't drawn the automobile, but there it is. The total mass of the car and piston is 3,200 kilograms. What force must be applied to the smaller piston to support the car? What we're going to see here is that if you want to lift a heavy object such as an automobile, which would require what I've drawn here, F2, you don't have to press with nearly as much force. You can apply a much smaller force, F1, and I'm going to show you why this is using Pascal's law. So let's press down with some force, F1, and that force of this piston, it's pushing on a fluid that is contained within this tube. And that fluid is going to push up on the piston on the left that has some cross-sectional area A2. Now we press down with F1 and it is spread out over an area A1. So the pressure that we cause, the pressure that we're adding into the fluid is F1 over A1. Now that pressure increase gets transmitted throughout the entire fluid. That's what Pascal's law says. And so whatever pressure we just increased is going to be F2 over A2. Now we're not going to care about the original pressure of the fluid because that's not going to have any effect on lifting the car. We're looking at the additional pressure. In a sense, with the previous equations, it's really the P naught that we're dealing with here. But that pressure is F2 over A2. Let's put these P's equal to each other because it's the same pressure. So F1 over A1 is F2 over A2. And this is going to translate into a greater force because there's a greater area. So there's my picture, my ratio right there. F1 over A1 is F2 over A2. Let's solve for F2. F2 is F1 times A2 over A1. Now what this means is that when you apply a force F1, you're going to get an output force that is F2, and that output force is, it corresponds to F1, so the greater force you press with, the more you're going to get, but that's going to be multiplied by the ratio of A2 over A1. So the greater the area on the left is compared to the area on the right, you're going to get a multiplication factor of the force that you applied. That multiplication factor, that ratio, is called the mechanical advantage. So if A2, let's say it is 10 times larger than A1, you're going to get 10 times the force. Now, let's say that A1 is 100 square centimeters, so that's a small pad, 10 by 10 centimeters, and A2 is 1 meter by 1 meter, 10,000 square centimeters. So we're going to maybe, we can step on A1 with our feet, we can stand on it, and we're going to put a car on A2. The force that we're going to get is F1 times the ratio of those areas. The ratio of those areas is 100 times. And so if I want to lift something, let's say the car, for example, in the example, the car has a weight, it says a mass of 3,200 kilograms. Okay, so that's a weight of about 7,000 pounds. All I need to do is push on the part on the right, the piston on the right, with 1/100th of that, with 70 pounds, and that will lift up the car. So we get a mechanical advantage because we get more force than we put into it. Now, with every mechanical advantage, there's always a mechanical disadvantage. So there are a variety of machines that we have in physics, and machines often are designed to give us a mechanical advantage. A lever does that as well. But there's always a disadvantage, something that we're trading off, something we're giving up. The disadvantage comes from the fact that the volumes, the change in volumes are going to be the same. So if we press down a certain volume of fluid on the right, we're displacing that fluid and it's going to show itself right here. Well, the change in volume on the left, delta V2, is equal to the change in volume on the right. So follow me through with this with the geometry. Delta V2 is the area 2 times the height that piston is going to go up. We'll call that delta Y2. Delta V1 is area of 1 times delta Y1. So if we solve for delta Y2, which is how high that piston on the left goes up, is equal to how much distance we pressed down on the one on the right, but that's going to be offset by the ratio A1 over A2. Notice it's the reciprocal of A2 over A1. So if, as in this example that I showed, we got a mechanical advantage of 100, we're also getting a height disadvantage of 100, which means we're going to press down on that piston. Let's say we press it down by 50 centimeters. Well, the piston on the left is only going to come up by 1/2 of a centimeter. So that is the trade-off when we get a mechanical advantage. And that is the end of section 15.2, hydrostatic equilibrium. Have a great day.